It's gotten real quiet in here, so I think that means I'd better turn on the microphone and start talking. My name's Tim Swindle. I'm the director of the Lunar and Planetary Lab here, and I want to welcome you to the first of our fall lecture series. Before we get going on the lecture itself, let me put in a few ads for some other things going on around here and around campus. First, the astronomy department, or Stewart Observatory, across Cherry Street from us, has a series of lectures. They do them about every 2 weeks, and you can get, they have flyers, we have flyers for them out in the atrium outside here afterwards, if you want to pick one of those up. The next lecture is September 30th, and it is on the brightest galaxies in the universe. We have, as I mentioned, this is a lecture series. We do it once a month. So the next one, normally we do it in the middle of the month, but next month we're doing it October 30th, because that is the 75th anniversary of the Orson Welles radio broadcast of The War of the Worlds. And so that will be the topic, and we will play the radio broadcast for you afterwards if anybody is interested. And I'll be doing that one. I'm sorry, I'm a War of the Worlds geek here. And then our third lecture of the fall will be by Professor Joellen Russell, talking about how the Antarctic is helping Arizona keep its cool, and that one is on November 13th. Some other things going on September 25th, which is, so it's a week from today. There's a movie coming out. It's a unique blend of documentary, alternative history, and science fiction thriller called Europa Report, and about a contemporary mission to Jupiter's moon, to Europa, to investigate the possible existence of alien life. The admission fee is $750 for students. I don't know what the regular fee is. But anyway, as a part of that, afterwards, Dr. Veronica Bray of LPL is going to be doing a Q&A about Europa. And there's more information about that on the Lofts website. Also, our graduate students and other graduate students around the College of Science are doing a variety of things. We have a movie coming up. We've been running some movies. We've done the first two outside. I'm not sure whether the next one will be outside in Highland Commons or will be in here. But the next one will be the day after tomorrow. But the date is, do you happen to know? I realize it's being run out of geoscience. Yeah, it's the geosciences department is putting that together, their grad students, and it's probably about 3 weeks from now, something like that. But if you want to be on our mailing list, you'd probably find out, and if you want to be on our mailing list about this sort of thing, you can sign up for that afterwards, outside in the atrium. Just talk to Maria Schuchart, who will be out there. And the last thing I wanted to plug in the commercial sense is that we are going to have an art show. And James?
Yeah. So as part of this grad outreach that we're doing here in the Lunar and Planetary Lab, we're actually going to be putting together the Art of Planetary Science, an exhibition of art that's both inspired by planetary science, so actual pieces of art, paintings, sculpture, things like that, as well as scientific data that people can interpret as being art, so beautiful images, maps, things like that. And so this is actually an open competition for the general public. It can be amateur painters, amateur astronomers, what have you, and there will be a competition component. So any one of you can enter. There'll be prizes from Bookmans, Posner's, Sarnoff Art, Adobe software, variety of different things. And just recently, to top the cake off, select pieces of the show will go on to a special event at the Tucson Museum of Art. So I encourage any of you who have artists friends or artists family or artists yourselves to submit something. I'll be outside after this lecture with flyers and business cards if you have questions. Thank you.
And the event itself is December 4th. Okay, thank you, James. And that was James Keene. I didn't do the intro well, sorry. Okay, and now for the main event. Our speaker this evening is going to be Ed Beshore. He's currently the Deputy Principal Investigator for the OsirisRex mission that will be returning a sample of an asteroid back to Earth in about a decade's time from now. And Ed has had an interesting career here. His first planetary science work was with one of the Pioneer spacecraft in the 1970s. Were you still an undergrad here at the time, or just graduated? But in his first life at the U of A, he then went off and spent a couple of decades as a software engineer. Had his own technical marketing company for a while. At some point, he built his own observatory, just became an amateur astronomer. But then when his wife wouldn't let him buy a bigger telescope, he came back to U of A and started working with the telescopes in the Catalina Sky Survey, the asteroid hunters, and became the survey operations manager there. And that is an operation that I'm sure you'll be talking about, but it's a very, very successful operation. And then moved on to the OsirisRex mission project. And so without further ado, Ed Beshore.
Well, thanks a lot, Tim. I really appreciate that. It's really a great honor to be here on this first night of the new season of the LPL lectures. These are really a great series. It's a great venue to hear about what's going on in planetary science from the people who are really making it all happen. This is really one of the centers of the world for planetary science. So this is a great place to learn about this stuff firsthand. So my talk tonight is what's up with all the talk about asteroids. I don't know if you've noticed, but over about the last year or so, they've been in the news quite a bit. It started about in February 15th. There was going to be a flyby of a little asteroid called 2012 DA14. Great name. That was 20 or 30 meters across, but it was going to fly only 17,000 miles away from Earth. That's not as high as our geosynchronous satellites orbit the Earth. So that was a bit of a newsy item. It happens from time to time, but it was a good opportunity for us to talk a little bit about how good a job operations like the Catalina Sky Survey have done in finding these objects. But we got upstaged on that very day when a 20-meter wide asteroid came in over southern Russia, exploded over the town of Chelyabinsk, did millions of dollars worth of damage and injured 1,000 people. So that really captured the news and set off a vigorous public debate about what we ought to be doing about these things. Now, in fact, we've actually been doing a lot of things about this problem for a long time, and we'll talk a little bit about that tonight, but that really started the discussion. In addition, NASA has been looking for the next job that they should do with their manned space program, and one of the ideas that they've come up with is to fly to an asteroid with a robotic mission, retrieve it, bring it back to the vicinity of the Earth, and send men to it where we can study it more closely. So I thought we should be talking a little bit about what's up with all this stuff, what's going on. So I thought before we got started, we would just talk a little bit about the history of asteroids. What do we know about them? What are they? How did we get there? I also wanted to make sure, because this is the inaugural lecture for this year here at LPL, is talk quite a bit about the role LPL has played in understanding asteroids better. So this guy is Giuseppe Piazzi. It's an image of him. He was a Catholic priest. Oftentimes priests were also astronomers. They were curious, they were learned, and maybe they had plenty of time on their hands to look through telescopes. And Giuseppe Piazzi was looking through a telescope one night, developing a star chart, and he saw an object in a field of stars that he thought looked like it was new. And so what he probably saw is something similar to what you see here over the course of a couple of nights, an object moving against the background of stars. Now, Piazzi thought that this was probably a comet, and what happened is he watched it for a month or so, and it disappeared into the glare of the sun. And when he went to find it after he thought it might come back out from behind the sun, he couldn't find it anymore. And part of the problem that he had is that he didn't have a way to come up with an orbit for this object. He didn't have a mathematical method to predict where to look for this thing next. Now, Kepler, in the 1600s, 150 years before Piazzi found Ceres, showed us that all things orbit the sun in ellipses. So this is an ellipse for the asteroid called Apollo. So we got the sun here, and you can see some of the inner planets circling around on the inside, but you can see very definitely that's an ellipse. A circle is just a special case of an ellipse. And so this shows us that orbits can be described mathematically, and if you can kind of come up with that mathematical description of the orbit, you can start predicting where these things are going to be. And that's what you really need to do if you want to start developing an inventory of asteroids, if you really want to start accumulating them. You've got to be able to predict where they're going to go. But the trouble is Piazzi didn't have any way to do that with just a few observations that he took through a telescope. So this guy, Carl Friedrich Gauss, was sort of kind of paying attention to the news, and he heard about the discovery of Ceres, and he knew about the problem in trying to recover it, and he thought, you know, I'm going to sit down and figure out how to do this. And well, if anybody could do it, Carl Friedrich Gauss could, because this guy was a bona fide genius. Any student of physics, over the course of their 4 years of their undergraduate education, will encounter this guy a lot, because he has been involved in mathematics, geodesy, geophysics, electrostatics, astronomy, optics. I mean, Gauss has got his fingerprints all over everything. And in just one short year, he was able to come up with the method for transforming a set of observations taken on the sky and turning those into an orbit. And that was a breakthrough. Once we had that, we could really start assembling our catalogs. But there was one other thing that was important. Our atlases were really bad. We didn't have any road maps in the sky. All we had were these beautiful atlases. I mean, this is gorgeous artwork, but it didn't have very many stars. There weren't very many faint stars in it. Their positions weren't necessarily all that good. And so you really didn't have a road map. It'd be like trying to find a town with a really crummy hand-drawn map. You really needed a better set of charts. And so the next innovation was the development of something called the Bonner Durchmusterung, which basically is the Bonn Observatory survey. That's what that means. And it was just a catalog of very precise positions of about 325,000 stars. And that allowed the production of charts that could allow you to look through a telescope, see what was there, and compare it with the chart and see if there was anything new. This really allowed the discovery of asteroids to take off. And this, indeed, the BD, was the basis for all atlases up until about 1966. So it was really quite a good product. And with the availability of a good atlas, about 2,300 asteroids were discovered by 1959. So some of the things that were discovered about asteroids after we started to accumulate some information about their orbits and that sort of thing was that most of them reside in an area between the orbits of Mars and Jupiter. We call that the main belt. Now what this is a simulation, or it's not really a simulation, it's a model that shows about 200,000 asteroids in it. They're not to scale. Each one of these little dots is about 1 million times larger than it really ought to be, because if you looked at this, you'd think, how did we ever get a space probe out past the orbit of Mars? We just run into this green wall of asteroids. But most of them reside out here, and they're very, so that means that, first of all, we're safe. They stay well out of our way. There are a few objects that find their way into the inner solar system. This is the orbit of Mercury and Venus and Earth and Mars. And some of these things are getting kind of close to the Earth here, and those are troubling, and we'll talk about those a little bit more in a bit. We think that asteroids are really the result of collisions that occurred in the main belt of larger planetesimals that were formed there when the solar system came together about 4.5 billion years ago. So we think there are these collisional remnants. Most of the time they spend their time out here in the main belt, but through certain forces of radiation pressure and interaction with the gravity of the giant planets, Jupiter and Saturn, occasionally they find their way into the inner solar system, and that's when they become problems. But after we had about 2,000 or 3,000 asteroids in our catalog, a lot of astronomers began to lose interest in them. First of all, telescopes were getting bigger. They were starting to look past the solar system to see really marvelous things in deep interstellar space. And they were taking very long images with their photographic plates. So we were using photography attached to our big telescopes. And sometimes we would spend the entire night taking just one image, letting the light accumulate and grow on this photographic plate so we could see the faintest things, and then it would be ruined. by something like this. And asteroids began to be called the vermin of the skies. And I never really quite realized what they meant by that until the first night I started working on the Catalina Sky Survey, and I looked at a field where there was a lot of asteroids, and they were all kind of just crawling around on the field. It kind of reminded me of the first time when I moved into an apartment not too far from here, and walked into the kitchen after midnight and turned the lights on. And so I kind of understand how that moniker came along. So let's move along then and say that not everybody thought that asteroids were uninteresting. And not everybody thought that the solar system was uninteresting. And this gentleman, Gerard Kuiper, was a Dutch astronomer who came to the United States, to the University of Chicago, and he was interested at the get-go from about the moon. He was also a great observer. He came to Tucson and started the Lunar and Planetary Laboratory just over 50 years ago. And like I say, he was a great observer. He discovered moons of Uranus and Neptune. He discovered carbon dioxide on Mars. He discovered methane on Saturn's moon Titan. He was really the quintessential observer. And it turned out he was a pretty good salesman, too. And he could work very good with NASA. And that was important because just about the time he founded LPL, Kennedy announced that we were going to send men to the moon. And they started looking around for experts, and there weren't that many of them around. But Kuiper was here, and he was very interested in the moon, and he was interested in assembling a lunar atlas, which was badly needed. So he established a very close relationship with NASA. And on your way out of the building tonight, if you stop by the elevator down on the ground floor, there's a plaque right next to the elevator that shows that this building was built by NASA. I believe it was 1965, something like that. And it was really to pursue and support the research that was necessary in order to make the manned space program possible. So there was a comeback. As we began to really start looking at these things a little bit more closely, asteroids started to get a little bit more interesting. And one of the guys who really pioneered this work was a fellow that also worked here. His name was Tom Garels. He came to the Lunar and Planetary Lab with Kuiper. He was also a Dutch astronomer, and he was quite a character. When he was 10 years old, he would get on a horse in his home in the Netherlands, and he would ride for days just sleeping in people's barns. So he was developing curiosity and courage that would serve him well just a few more years later, because as a teenager, he worked closely with the Dutch resistance. He came to England and then was parachuted back into the Netherlands to help Dutch resistance fighters. So he was doing this when he was 16 or 17 years old. Quite a guy. He was also the principal investigator on the Pioneer 10 and 11 missions, which gave us our first close-up look at Saturn and Jupiter. He was very interested in polarimetry, looking at how the stars and the planets are polarized. If you've got a pair of polarized sunglasses, you can do that, and you can watch the color of the sky change when you do that. He was very interested in that because there's a lot of scientific information that you can get out of that sort of thing. He was also quite a driver. People have a lot of stories about Tom's driving. And so he would observe all night long up on Mount Lemmon, and then he would come down the mountain like, going 100 miles an hour, sometimes on two wheels. And when people asked him why, he'd say, well, because it helps me stay awake. I'm tired. I've been up all night, and I need an exciting ride down. So Tom was quite a character. And he was also interested in asteroids, but I should also say Tom passed away just a couple of years ago. And in recognition of his service to the Dutch military, the Royal Dutch Air Force staged a flyover right down the campus in front of the Lunar and Planetary Lab for Tom. One of the other aspects of Tom's legacy is the Space Science series. Tom was the original editor of these, and this is a series of books, and I should have brought one with me. They're really thick. They're great for pressing flowers, but they're also good reading, too. And these things really represent the state of the art in what we know about solar system science. And so Tom was very involved in the development of this series of books, and I'm going to use these a little bit as touchstones of the development of our understanding about asteroids as we kind of go through the history of Lunar and Planetary Laboratory and our understanding of asteroids and how it evolved over time. So the very first book that I want to talk about is Asteroids, edited by Tom Garels and published in 1979. And this really started to assemble some of the things that we knew and suspected about our emerging understanding of the asteroids and their role in our understanding of the larger solar system. We were starting to understand their compositions a little bit better, the fact that asteroids actually live in little families, they're little dynamical families. They evolve similarly, and the way they evolve dynamically can tell us something about how the solar system was formed. So this book was published in '79. So I'm going to shift gears a little bit now and talk about another aspect of asteroids that developed it was really starting to come around in the 80s, but this book, well, I should say this book right here, was published in '94, also written by Tom Garels, to talk about the role that asteroids played as dangers to the Earth. Tom recognized, along with several other scientists, most notably another Arizona scientist at the USGS, the U.S. Geographical Survey up in Flagstaff, his name was Gene Shoemaker, really felt that we were not paying close enough attention to these things as potentially dangerous objects, things that could really have an effect on civilization. So this book really summarized our understanding, our scientific understanding of the role of asteroids and their danger to the Earth. Now, if you're looking for proof that the Earth gets hit by asteroids, all you really have to do is look at the moon. By the way, the moon was gorgeous tonight for those of you who might have come in. It was a beautiful full moon tonight. But you can see here that our nearest neighbor, which is only 250,000 miles away, that's really in our backyard, has been pummeled by objects over its 4.5 billion year history. The reason we don't see this kind of evidence on the Earth is because wind and water conspire to erase the evidence of these impacts in the past. But nevertheless, it's clear that the moon has been subjected to a lot of impacts. But if we look around on the Earth, we can find evidence of impacts here too. There's 3 of them right here. One of them you might have been to. This is the meteor crater in northern Arizona. How many folks have been up there before? It's a great trip. And if you haven't been to Meteor Crater, it's worth going up for it. This is about a mile wide and around 500 feet deep. It was created about 50,000 years ago when a 50-meter wide iron meteorite hit the northern Arizona plateau. And if you happen to be a woolly mammoth lumbering around up around Winslow, it was a bad day when this hit. But this is actually a really great place. As one of the geologists up there told me, you couldn't ask for a better place for a meteor to strike the Earth because you have these beautiful layers like you see in the Grand Canyon. This is really very much Grand Canyon geology here. And you hit it, you see all these beautiful layers exposed, and it also shows you the dynamics of what happens when these things hit. And this asteroid was traveling at about 10 miles per second when it hit the Earth. So even 50 meters in size, that's something on the order of the size of this building, hitting the Earth at 10 miles per second is carrying a huge amount of energy. And so you can really get a good sense of what even a small object can do when it hits. Now this object right here is called the Manicouagan Impact Structure. It's in Ontario, Canada. This is when a 3-mile wide asteroid hit. This crater is about 50 miles across. And in fact, this is one of the largest hydroelectric reservoirs in Canada. So it's a huge lake. And even though it hit 250 million years ago, it hit in solid granite. So this crater has survived. It's been ground down so it's almost flat. And so it's actually a little smaller than it was originally. But it's definitely evidence that the Earth has been hit not only by small objects, but by really big ones. And then there's this one. Now this kind of goes to my dinosaur joke at the beginning of this section. This is an underwater gravity map that shows where the gravity changes at the base of the Gulf of Mexico, just off the Yucatan Peninsula. This is one of the many pieces of evidence about a 6-mile wide asteroid that hit the Earth about 60 million years ago and likely took the dinosaurs out. There's a strong scientific argument in support of that theory.
I have a question, Ed.
Sure.
Is there a coincidence these are all 3 in North
No, because there's other places around the world, like the Vredefort crater in South Africa, a very large one there. So I don't believe so. It's just, I guess that's where it was easy to look. But what we did find is that there's ample evidence that this occurred and that there was global effects. And it turns out that what we believe now is that anything on the order of about 1 kilometer in size or larger really could have devastating effects on the Earth if it hit. It could change the climate. It would throw up hundreds of billions of tons of soil and water into the upper atmosphere. It would change the climate for several years. The food chain would break down. And if you were a dinosaur, you wouldn't have anything to eat. And likewise, us human beings would be badly affected. This could be a civilization or a disrupting or a civilization-ending event for a very large object. So it's certainly in our interest to see if we can find these things. Now, I showed you stuff that's like 50,000 years ago, 250 million years ago. It's like, okay, no worries. Well, actually, there's current reasons to be concerned that this stuff happens. Just 100 years ago, an asteroid blew up, or perhaps a comet fragment, blew up over northern Siberia and flattened 80 million trees. That's amazing. Now, fortunately, it was in a remote part of the world. I don't even know if anybody was injured by this, but certainly it registered on seismographs in London. Fires occurred that could be seen for hundreds of miles, and the evidence of all these trees being flattened, is stark evidence that something, very destructive hit. And then, of course, the Chelyabinsk event, where we suffered some serious injuries and some serious monetary damage. And if this object would have come in at a more direct angle, it came in at quite a slant angle. If it would have come in at more a direct angle, there's reason to believe the damage would have been much, much worse. And this was only something on the order of 20 meters across. So again, you take that mass, but it's the velocity that really matters, because to come up with the energy of this, you square it. So if the velocity is at 10 meters per second, it goes like the square of the velocity. So that's why these things can be so destructive when they hit. But I should tell you that this sort of thing happens pretty frequently, about once every 50 years for something about this size. The truth is, though, the Earth is 2/3 water, and even today, most of the landmass is empty. So the danger from actually getting hit by one of these things is pretty low, or certainly comparable to the kind of danger that we experience with earthquakes, hurricanes, flooding. So it's really a public policy issue about how you want to deal with these small objects. But the large ones probably really does pay for us to try and find them. So enter Tom Garels one more time. Tom proposed the Space Watch program. As early as 1980, he and Bob McMillan came up with the notion of an observatory that was dedicated to the search for these objects. And by 1989, they were actually in progress looking for things. They were the first survey to ever find a near-Earth object using a modern electronic detector. And they were very, very productive through the 80s and 90s. And today, they are still operating, but their role has changed somewhat, principally away from discovery to the also important problem of keeping track of the ones that we've already found. It does us no good to discover these things if we only lose them. And while we get orbits, we have to tweak them every so often. We have to touch them up. So another observation will help us refine those orbits, and that is what Spacewatch has been so very valuable for in the most recent decade. But today, Spacewatch still operates and is a very productive and very important part of the surveying for asteroids, and this is an LPL program. The other program is the Catalina Sky Survey, which Tim mentioned and is very much still something that's my heart's warm about, because this is how I got back involved in astronomy just about 10 years ago. It was started by Steve Larson along with some students in 1998. It was refitted with some state-of-the-art electronic detectors right around 2000. And since that time, the Catalina Sky Survey has been literally the most productive survey of all of them. I haven't checked for the total last year, but it's somewhere between a half and 2/3 of objects discovered, of all objects discovered, was discovered by the Catalina Sky Survey last year. This was started with by Steve Larson. Steve's another long-term alum here at the Lunar and Planetary Laboratory. He was an undergraduate when he started working for Gerard Kuiper, taking images of the moon for that consolidated lunar atlas that I told you about that NASA needed in order to explore the moon during the manned missions. So Steve's also been a long-time contributor here at the Lunar and Planetary Laboratory. And this is an image of the 60-inch telescope that's at the top of Mount Lemmon. Catalina started out with 3 telescopes, one on Mount Lemmon, a 60-inch telescope, a slightly smaller one on Mount Bigelow, as well as one in the southern hemisphere in Australia, because you can't see the entire sky from here in Arizona. You can only see about 2/3 of it over the course of a year. So having that additional telescope in the southern hemisphere was very important in being able to find objects that weren't visible in the northern skies. So, in addition to our ground-based work, we've also visited many asteroids and comets with spacecraft. Most of the time, we were on our way to somewhere else, and we just happened to be able to zoom by an asteroid and take a few tantalizing images on our way. In other cases, we actually had some missions that were targeted, that were going to go directly to a comet. In this case, this is Comet Halley. That's actually an image taken by a spacecraft that went to Comet Halley. Gosh, I think it was, what was it, 1986, is that right, Rick? Yeah. So we can see that they come in all shapes and sizes. Some asteroids are pretty much stony objects, mostly made of rock. Others are made of nickel and iron. They're mostly metal. Asteroids come in, like I say, very well. There's a comet. That's a fairly weird shape. But this guy, Eros, that's a really odd-looking character. Some are starting to get a little bit more round, and this one is Matilda, and it was visited by the NEAR spacecraft several years ago in the 90s. So we've gotten some good looks at the asteroids, but like I say, the glimpses have been tantalizing and informative, but short. And some of the things that we really want to know about asteroids, we can only learn if we go and bring a sample back. So, life goes on. We learned a whole lot more. That first Asteroids book came out, then Asteroids 2 was released, and then Asteroids 3 was released. And I just got a note about 6 months ago, Asteroids 4 is in preparation. So we're learning a whole lot because we're publishing a lot of pretty heavy books about these things. So we know a lot more. And one of the things that we think we know about asteroids is how useful they could be in helping us understand the evolution of our own solar system. This is a remarkable image, and I love to show this because, as some of you may know, stars evolve. They eventually destroy themselves and then are reborn as stars. This single image shows the entire lifespan of a star in one image. This is not doctored. This was taken by the Hubble Space Telescope. And what we're seeing here are very bright blue-white stars that are burning up their fuel really quickly. This is why the hotter they burn, the faster they burn their fuel. And eventually they begin to get unstable, and they start throwing off their shells. They start to pulsate, and you can actually see one star here. It's got a ring around it, and it's blowing off material from each of the poles. It's blowing material into space. Eventually, this star is going to go supernova, and it's going to create elements, all of the elements in this room, the elements that you and I are made of, everything that we pick up and work with and walk on is material that was one day, long ago, forged in the middle of a star by a supernova. We are made of star stuff, as Carl Sagan said. And that is what is getting ready to happen here. When it happens, it blows this material into space, and you get these beautiful clouds of dust and gas. And sure enough, after a while, they start to congeal again under their own gravitational force. They start to come back together again. And right here, you see something that's called a propylid. There's one there, too. These are little germinal solar systems forming. These are stars and planets collapsing, and the process begins all over again. We would like to find out what that material was like. because we are trying to answer some very basic questions about things here on Earth. As much as you might think we know where the water came from, we don't really know for sure. Where did the water come from on Earth? Was it in one of these little propylids from the beginning, or did it get delivered from outside the solar system? Did it get delivered from elsewhere in the solar system by meteors or comets? How about the organics, the things that really are the stuff of life? Do we find the base pairs for DNA in this material? How could we find something that would represent the material that we'd see in this newly forming solar system? Well, it turns out the asteroids are perfect for this. They're really the leftovers, in many ways, of the construction of the solar system. And a particular group of those asteroids, called the carbonaceous asteroids, are particularly interesting in that way. We think the carbonaceous asteroids are really the leftovers from the beginning of the solar system, 4.5 billion years old. It's like walking into a kitchen and finding a loaf of bread sitting on the counter. And what you really want to know is, how did you make the bread? And you look around and you notice that there's some flour on the floor. It's that's the way the asteroids are in a way. They are some of that remnant building block material that ultimately we think could give us some of the secrets about how the solar system formed. So in May of 2011, the University of Arizona and the Lunar and Planetary Laboratory received the largest grant ever, $800 million from NASA to fly a mission to an asteroid and bring back a sample of one of these primitive carbonaceous asteroids. It's called OsirisRex. The project is called OsirisRex, and it stands for Origins, Spectral Interpretation, Resource Identification, Security, Regolith, Explorer. It's a mouthful. But it really is a representative name, because we are looking for our origins. We are going to interpret this using spectral data to try to understand the material that it's made of. We're looking to see if there are resources that we might one day be able to take advantage of from the asteroids. And we're going to understand the role that asteroids play in our security. It turns out the asteroid that we're going to, an asteroid named Bennu, is the most dangerous asteroid we actually have on the list right now. 1 in 1,800 chance of a collision with the Earth late in the 22nd century. We're going to try to understand a little bit better whether that threat is real or whether we can take it easy. So the spacecraft is, I'll see if I can get this animation going here. This is going to be so this is our spacecraft. It has a sample return capsule and a science deck on the top. And that's where our scientific instruments are at. 2 large solar panels for power, a propulsion system on the bottom, and a large high-gain antenna for communications with the Earth. And we're going to send this asteroid to the planet, or rather the asteroid Bennu, in 2016. That's when we launch. We're developing all the science instruments with other institutions. The cameras are being built right here at the University of Arizona. The science is being put together and organized here at the University of Arizona under the direction of Principal Investigator Dante Loretta. And we are also going to be running the science mission from here at the Michael J. Drake building just a few miles from the campus. So I'm going to show you very quickly another animation that shows you what we're actually going to do. And this is actually an animation put together by the Goddard Space Flight Center, who is one of our partners in putting this mission together. Let's see here. So we actually arrive at the asteroid in 2019, or in 2018, late 2018 in the fall. And the first thing we do is we start making maps. We circle the asteroid for about 180 days, making maps, taking spectra, trying to look for a good sample site. We have, again, the science instruments on the deck, camera systems. We'll have spectrometers. We'll have what's called a LiDAR system for measuring the topography on the asteroid. So we're going to get a really great set of maps so that we can make an informed decision about where to get that sample. When we find a sample site, we're going to jettison this cover and this thing called the TAGSAM, the TAGSAM arm, the touch-and-go sample acquisition mechanism will come out. Now, it looks kind of like an air filter off of an old Firebird. But what's going to happen is we're going to very carefully approach the asteroid at just 10 centimeters a second, touch it fire some nitrogen gas which will fluidize the regolith, the loose soil on the surface, and capture it in this filter. We're going to get at least 60 grams, but in testing we've gotten almost 2 kilograms. That sample head will be put inside of a sample return capsule and an explosive bolt will be fired. That sample head will be released, the sample return capsule will close, and the spacecraft will begin its journey back to Earth in 2021. It'll arrive back to Earth in 2023, and that sample return capsule will be released. The spacecraft will be redirected so it will not hit the Earth, and the sample return capsule will come down in Utah, just outside of Salt Lake City, at the Utah Test and Training Range. So we're a partnership of the Lockheed Martin Company, the Goddard Space Flight Center, and the University of Arizona. Those are the principal partners putting this project together. So I'm going to wrap up by talking of one more item in the news, and that's this whole notion of sending a man to an asteroid. Is this a good idea or not? And this is sort of my personal perspective on things. This is what we were doing with men in space about 50 years ago. This is the launch of a Redstone rocket carrying Freedom 7, and the astronaut, Shepard? Yeah, Shepard was on it. And we just sort of lobbed him in this ballistic trajectory out about 50 miles high and 500 miles downrange. That was about the best we could do. And we got pretty lucky because we were blowing rockets up right and left at this point. So this is what we could do 50 years ago. This is what we can do now. So we now have a permanent presence in space. There are 6 astronauts living in the space station. This is one of my favorite images because it's one of the few that actually have a picture of a shuttle docked with the space station. We've been operating this for 10 years. We're going to operate it for another 10 years. We're really getting our experience in space here. But this is near-Earth space. This is low Earth orbit. We're starting to get this figured out. So what is the next thing that we ought to be doing? A lot of people would like to have us go to the moon. A lot of people would like to have us go to Mars. I would love to go to Mars. But it may be too ambitious a next step. One of the things that NASA has suggested that we might do is to actually send a robotic spacecraft to a small asteroid and retrieve it and bring it back into near-Earth space. And it's not a crazy idea. From the standpoint of defense, if we're ever, one of the most common questions I got on the Catalina Sky Survey is, what are you going to do if you find one? And, well, I'm going to start writing bad checks and drinking all the good wine. But if you really want to do something about it, you're going to have some capability to live and work in space. You're going to have done this before. And if we actually practice using systems like this, perhaps this is indeed the right move if we really want to develop our capabilities to defend the Earth in the event that we find an asteroid that's going to strike us. Resources. There's also been a lot of discussion about the resources that we might find in space. Most asteroids are rock, but they also have large amounts of platinum group metals in them. In fact, if you took some of the asteroids that we've seen in space and some of the meteorites that we've found on the Earth, and you stuck them in the Earth, and a guy came along and mined that and did an assay on it, they would mine that asteroid. I mean, there's valuable concentrations of platinum group metals in some of these objects. We don't really know whether it's ever going to be practical for us to go retrieve these in space. But I've been looking at this problem a little bit myself because I'm learning about how you build spacecraft. And we've got a long way to go, but I envision a fleet of small, unmanned, robotic explorers that go out and start doing surveys of asteroids and looking for these things and reporting back and moving on to the next asteroid. We're going to do something like that with OsirisRex, and we already have another spacecraft out there called Dawn that's visited one asteroid, Vesta, and it's moving on to the next one. So we've got some of the pieces that we could put together to really make a very potent little armada of spacecraft that could go out and look for these valuable asteroids. And then perhaps this retrieval technique might be able to inform us of how we might grapple onto one of these things and move it back to the Earth. Very slowly, over a period of maybe tens of years, maybe even 50 years, it could be worthwhile eventually. So the other thing is that asteroids might end up being filling stations for extraplanetary travel. These things have water in them. Perhaps we can find a way to extract that water. Water, of course, is important for human beings if they want to live and work in space, but water can also be the basis of rocket propellant. And if we find a way to be able to extract the water from these things, these could effectively be filling stations on our way to the stars. And indeed, I think that one of the things that I think is very interesting is that these things started out as vermin, and they may well end up becoming our stepping stones to the planets and the stars. So thanks very much, and if you have any questions, I'll be glad to try and answer them for you. Yes?
So was the asteroid that hit Russia in February, was it anticipated by the mapping?
So the question was the asteroid, the Chelyabinsk asteroid that hit in Russia, was that seen? Did we know that was coming? No, we did not. We have found, the Catalina Sky Survey and other surveys routinely find objects of that size. That was not, in fact, they've found objects much smaller. This object was coming out of the sun, in the sense that it was coming from the direction of the sun, from the glare of the sun. So it would have been impossible for any ground-based survey to have seen that object before it hit. There are proposals, and there actually is a survey that's going to be put online called Atlas, which is going to be designed to look for these objects just days before they hit. Now, the object of the survey would not be to divert the asteroid, but you could at least tell people, don't go close to your windows, because that's what happened in Chelyabinsk, is everybody saw this thing fly over, and they were standing at the windows, and then 2 minutes later, the sonic boom hit and blew all the glass out of the windows. That was most of how people were injured. The Catalina Sky Survey, actually in 2008, was the first to discover an object of this size, 2008 TC3, that did hit the Earth. And one of the observers, Rich Kowalski, actually was the fellow who was observing. He found the object, got some follow-up data, sent it into the Minor Planet Center, which does all the orbit calculations, and went to sleep. And I got an email from one of the folks at JPL, and they said, you've got an object that's going to hit the Earth. And it's like your first question after you hear that is, when? And he said, this afternoon. And that was pretty unnerving, but he was very quick to say, it's small. And this object was only about the size of a car. And this was discovered at 300,000 miles away, an object the size of a car. But it was well positioned, and so that was an example of how these things could be found, even these small objects. So, any more questions?
Thank you. If you identify an asteroid that looks like it is coming towards Earth, a fairly large one, what other techniques and methodologies is anybody studying what we're going to do about that?
Yeah, well, there's that question. What are we going to do if we find one? Yes, they are. As a matter of fact, NASA's started investing rather heavily in this. And there's a lot of approaches. There's techniques which we call gravity tractors, where you literally just have a spacecraft go out there and sort of station keep with the asteroid, and actually just the gravitational force of that spacecraft in the vicinity of the asteroid would change the orbit. But the key really is how much time do you have? If you have just a few years, you may have a very difficult time mounting a defense. The object of the asteroid surveys like Catalina and Spacewatch are to find these things early enough that we can actually put together a defense. And it could be a nuclear weapon, that not to break the object up, but literally to explode it in the vicinity of the asteroid that would vaporize the surface down to for about an inch or two of the surface. That vapor flying off of the asteroid would act like a rocket thrust and shove the asteroid over. You could paint the asteroid white. And I'm sure the Seidlitz company would love to pay for that. And it would literally change the radiation pressure on the space or on the asteroid, and solar radiation pressure would change the orbit. So you could do that in some sort of a calculated way and perhaps change the orbit that way. So there's a variety of ways that this could be done. Actually, there was a proposal for a short while, I don't think it's going to fly, to send an impactor to our asteroid, Bennu, so that our spacecraft could observe it. After we were done getting our sample, we would actually watch an impactor hit it, and there was actually a reasonable chance that impactor could change the orbit of the asteroid significantly.
How big is Bennu?
Bennu's 500 meters across, so it's pretty good size. But despite that, the force that our spacecraft will feel at the surface of Bennu is about a 10 millionth of the gravitational force that you feel when sitting in your chair here tonight on the surface of the Earth. And that represents some significant technical challenges for our mission, because actually flying around a small object like this is hard, because we have to have these very little tiny thrusters that just give us a few ounces of thrust, and the uncertainty in the amount of thrust that they give us. So in other words, when we fire one, they don't fire exactly the time we want them to fire, and they don't fire with exactly the thrust we want them to fire. And that uncertainty is actually creating some problems for us in our navigation plans. We're going to solve them, and we've got a very good lines on how to do that, but it actually turns out to be kind of a hard problem. Yes, sir.
Would you describe the Kuiper Belt as containing asteroids, or?
Yeah, you know, we really never talked very much about some of the cousins of the asteroids. There are objects in a belt outside of the orbit of Pluto in an area called the Kuiper Belt that very likely there are asteroids out there. We believe that there's not nearly as many as we have in our inner main belt, because there's been a lot of dynamics going on, and a lot of those got scattered out. There's also a lot of larger objects that aren't planets, that are not quite asteroids either. You probably have heard about how Pluto got punked a few years ago. And it turns out Ceres, the very first asteroid that Giuseppe Piazzi discovered, also has got put into the same bucket of being dwarf planets. They're round, they're pretty good size, but we're sure that there's asteroids out there, and asteroids that are also covered with mantles of frozen water and methane and ammonia we know as comets. And their orbits occasionally bring them into the inner solar system. The sun warms them up, and we see these beautiful tails, and we call them comets. So there's a whole family of objects out there in the outer solar system that we didn't discuss at all tonight.
I came in a little late, so I'm sorry if you already said something about this, but there's been a lot in the news about these asteroids when they impact creating amino acids.
Mm-hmm.
And is there going to be attempts to study that in the OsirisRex or in any future?
Absolutely. This is one of the big questions that we'd like to address with OsirisRex, and this is why it's so important to bring a sample back. You know, when you build a spacecraft, you have to create these miniature, very sophisticated instruments that you can fly on a spacecraft, but you have strict weight and power limits. And so there's only a very limited number of things that you can do with an instrument on a spacecraft. If we could bring something back, we could study it in our laboratories, and that's what OsirisRex will do. In fact, it's going to bring back samples that will be studied in this building, right here, right in the basement of this building, and we will be looking for things just like this, the organics, trying to understand the source of water. And the thing that's really great about being able to do that is we'll be able to study these samples for decades. We're still looking carefully at the samples that were returned from the Apollo missions 45 years ago using techniques that nobody even knew existed then. And that's the same sort of thing that we'll be able to do with the OsirisRex sample. In fact, NASA has asked us to archive 3/4 of our sample for just that purpose, for future investigations. We're only going to, if we come back with the required 60 grams, we're only going to get 15 grams of that to study. And the rest of it will be archived for future use.
But is it pretty sure that all of these asteroids have organics in them?
I am not a chemist, and I can't answer that. Tim, you could probably address that yourself, because Tim's also a meteoriticist and understands what we find in meteorites.
Not all asteroids have amino acids, but many of them do, and so the ones that are mostly metal probably don't, but the ones that have the carbon in them, those probably do. But we know what meteorites do, but we don't really know what the asteroids are like because we haven't been able to measure them.
Right. Yeah, one of the problems about meteorites is they've been sitting on the ground. And so stuff could have crawled onto them. We really don't know chemically how they've been transformed. Water hits them, changes them. We really don't have the provenance in the art world kind of equivalent terminology of where this thing has been and where it came from. And so what we really want to do with a sample from the OsirisRex mission is study this thing from the ground, go get a sample and compare it with what we see from the ground and compare it to our own meteorite collections, and we'll learn a whole lot. Hopefully make our own meteorite collections even more valuable from what we learn from that. Yes, sir.
The OsirisRex is going to take a dusting
Yes.
of the surface. Is there a chance that some of that material, or a lot of it, may just not be actually from the asteroid, but may be stuff that's fallen onto the asteroid, or debris from impacts, micrometeorites and whatever that have hit it?
A very good question. There's a process in asteroids, we call it gardening, where micrometeorites hit the surface and it sort of churns it over. And it is possible that some of the material that we find on the surface of the asteroid would actually be transported from other places. That's one of the things that we'll be looking very carefully for when we start to do this survey work. We'll be doing very careful spectral surveys to try to understand the composition of what we're seeing on the surface, to ensure that we're getting something that we believe is representative of the asteroid rather than something that might have been transported from outside. And we should be able to tell that with the suite of instruments that we're flying on the spacecraft. But nevertheless, that is a possibility. One of the things that we know about Bennu is it flies by the Earth about every 6 years. Sometimes it gets pretty darn close. And it's not, one of the other things we know is it's only about 1 gram per cubic centimeter density. Well, solid rock is about 2.5. So there's probably big voids. Like most asteroids, Bennu is probably a rubble pile. It's probably a bunch of smaller objects kind of held together loosely by gravity. And when it flies past the Earth occasionally, that rubble pile gets moved around and it gets resurfaced. And so we think that there's probably actually some transport from lower areas in the asteroid, or there's some tilling, if you will, that will probably help mix things up a little bit, which may be good, and it may help to confuse us a little bit. But that's just one of the things that we'll have to deal with when we start doing our survey of the asteroid.
The samples that you bring back, you're going to get 15 milligrams?
15, our mission success criteria say 60 grams.
60 grams.
Right. We're going to get 15 for immediate study
15.
and distribution around to other scientists in the world.
Okay. Are most of the tests that you run on this non-destructive, or will you deplete that supply?
Some of it will be depleted in the process of studying it. That's why we're having a sample, an archive. But we're very hopeful that we're actually going to bring back quite a bit more.
Oh.
Of course, like I say, in microgravity testing, we've actually flown this TAGSAM arm, or this TAGSAM head, in zero gravity flights, or actually what we call microgravity flights. And we've collected as much as 2 kilograms with the technique. So the real question is, will we find abundant material for sampling at the asteroid? And that's one of the things we worry about and we're trying to understand a little better right now.
Mm-hmm. Thank you.
Mm-hmm. Okay.
Oh.
That's right. That's right.
Another question. The samples that you bring back and the 3/4 of the sample that'll be archived, how will that be protected for future use and for, considerably more distant access and use?
Part of the money in our $800 million budget is to actually establish a special laboratory at Johnson Space Center at the same place that the lunar samples are kept. So we'll be using, actually one of the curators on that project is a LPL graduate, Kevin Ryder, and he's actually setting up and planning for that laboratory right now. The mission will bear the cost of that laboratory for a few years, after which NASA will take over the cost of curation of those samples, the distribution of them to other researchers around the world. But we'll be using a lot of the state-of-the-art techniques that were really developed from the lunar missions for keeping those samples safe and unsullied by chemical interactions with atmosphere and water. Yes?
How exactly will the sample land on Earth?
Okay, it's using a technique. One of the things that we use, one of the words we use a lot in this business is heritage. NASA loves the word because it means you're not taking a risk, you're using something you've done already before. And we're actually using something that has heritage from 2 previous missions. So the sample return capsule that you saw actually flew, that same kind of capsule flew on another successful mission called Stardust, where we flew behind a comet and collected some material from a comet, just not very much of it. We just sort of flew behind and captured all the stuff that got thrown off, and then we put that in a sample return capsule, came to the same place, the Utah Test and Training Range, totally successful mission. It comes in, it's got an ablative heat shield on it, just like the old Apollo spacecraft had, so it'll blaze through the atmosphere, slowing down, throwing off its energy by sloughing off this ablative material, and then it will release a parachute. And it will land softly, we hope, in the Utah Test and Training Range in 2023.
Several years ago, there was a Japanese mission to an
Yes.
asteroid.
That's
and
right.
They
Hayabusa.
landed on it, and did they return the sample? And
They did.
if so, what's been learned from that, and how does this differ from your mission?
Yes, the Hayabusa mission went to a Japanese mission, went to an asteroid called Itokawa. And it was a hair-raising mission because they lost some of the reaction wheels. They lost control of the spacecraft. It rolled and tumbled on the surface of the asteroid when it came back. They lost a transmitter. I mean, it was a miracle that they got back. And they did get back with samples that were measured in micrograms. Now, I don't believe there's actually been a public tallying of the total amount of material that came back from that spacecraft. Yeah.
It'd be less than a milligram.
Right. So it was not very much material. But it was successful. And Dolores, do you know anything about how much stuff came back from that?
I think that's right, less than a milligram in thousands of particles.
Right. Little tiny particles. Now, the thing is, scientists are amazingly resourceful, and they can do an incredible amount of research with just little tiny microscopic samples of things. But I'll tell you, I really would like to have a chunk of Bennu to look at, to open up, to see the inside of, and something on the order of a couple centimeters across would be just perfect. There have been previous missions. It has been incredibly useful. It was not a carbonaceous asteroid that the Japanese mission went to, but they are planning another mission, and I think they're planning on getting to their asteroid at the same time we are, roughly. It's a different asteroid, but so we've got a space race going now. It's friendly. We actually talk to those folks a lot. We're trying to learn as much as we can from them. Also, there's a mission that's another exciting mission that's getting ready to go right now. It's called Rosetta. And the Europeans have been flying it. It's going to a comet. They're going to land a lander on the comet. They're not going to bring back a sample. But this lander is going to be on the comet when the comet activates. As it gets close to the sun and begins to vaporize material off, this lander will be there taking science data all the time. The Rosetta spacecraft will be orbiting around behind the comet, transmitting that data as well as taking other information. And I was just actually in Europe last week talking to the folks at the European Space Agency about this, and they're getting pretty nervous because the spacecraft has been almost 400 million miles away from the sun, so it's got very little power. So they've put it into hibernation mode and told it to wake up on the 20th of January of 2014. They haven't talked to the spacecraft in 3 years. And so on the 20th of January, they are going to be on the edge of their seats hoping this thing phones home. Yeah.
So is there a plan to keep the sample that you're returning environmentally preserved in a vacuum environment, cooled and all that?
Absolutely. Yeah. The curation processes for these are very sophisticated. Again, a lot of them developed for the space program. You generally keep them in an inert material or inert atmosphere, argon or perhaps nitrogen. I'm not really sure. I'm not a chemist, and I'm certainly not a meteoriticist. But yeah, this is part of the plan. In fact, one of the big documents that just recently got produced for our mission was the curation plan that shows how we're going to do this, what kind of materials we'll need, what kind of resources we'll require in order to keep this sample pristine for future users of the sample. Yes, everything that has been in space gets actually put on. I think it kind of reminds me of that scene from Raiders of the Lost Ark, you know, where they took the Ark and they stuffed it in a warehouse. There's a warehouse somewhere called Space Exposed Materials. And everything that's been in space that comes back to Earth goes to this place, to the Space Exposed Materials. It's not really a warehouse. It's also curated, but it's going to be, everything's going to be sampled and held back.
I think.
Oh, you got
Okay.
You got to let her ask.
She gets the last question.
Okay.
Actually, I just wanted to say kudos to the Catalina Sky Survey because I read just today in UA News that they discovered a 1 to 3 meter object.
Kilometer. Was that
It was reported as 1 to 3 meters.
Oh, was it 1 to 3 meters? Oh, I was thinking about the one I think it was Jess discovered that was big, right? How, it was like kilometer plus. We don't find too many of those anymore either. So we found a 1 to 3 meter object. So
Yeah, I mean, the 1 kilometer is cool, but 1 to 3 meters is pretty amazing
tiny.
to be able to discover.
That's about the size
So,
of these chairs.
Way to go, guys.
That's great.
Okay. Well, let's thank Ed one more time. And so thanks to all of you for coming, and don't forget, if you want some flyers about other lecture series, want to sign up for our mailing list outside in the atrium. We'll see you all next month.